Everybody, our problem tonight is very similar to an AMC competition problem back in 2002, I believe. Now, let's get just this triviality out of the way. If n is equal to 0, this expression here is equal to 0, and you could think of that as 0 squared, right? So without knowing anything else, it's possible this could be the largest perfect square. I mean, I wouldn't know if an expression like this was ever a perfect square, but you'll see that it's possible for it to happen. In fact, it can happen twice, at least by my analysis. Now, so what we do right here, we want to find the largest n such that n over 1066 minus n is a perfect square. So we just simply set the expression equal to an integer squared. And again, n and k are assumed to be integers. Now, some algebraic manipulation leads us to this statement. The algebraic manipulation is very straightforward. All right. Now, notice something here that's kind of useful as far as making a determination on what kind of algorithm we're going to use. Notice that k squared and 1 plus k squared are consecutive integers, but they're also the numerator and denominator of a fraction, right? So you see, this is automatically reduced, and if you'll allow me, I'll just say RED. It's a reduced fraction, right? The numerator and the denominator can have no common factors, right? These k squared and k squared plus 1 are said to be coprime, relatively prime. In general, consecutive integers are relatively prime. It's not too hard to show that. But now we'll just go with that assumption here that this part of the fraction is already reduced. That forces 1 plus k squared to be a divisor of 1066. And so this is our answer to the why question. Now, we're talking about divisors, so it's useful to write down the prime factorization of 1066. Now that takes a little bit of time. I made up the problem so I know what the prime factorization is, but the prime factors here are 2, of course, one of them, all right? And then the next one is 13, and the last one is 41, okay? And you guys can verify that, but I've double and triple checked it, so this is correct. So these are the only 3 prime factors. But notice, you guys may remember that there's a combinatoric sort of way about this. If you ink both of these exponents, you get the number of divisors. If you ink them and then multiply them together, and you're accounting for the possibility of 0 being an exponent, which corresponds to a factor of 1. So that's equal to 8. Right? A pretty well-known fact from number theory that you can just take the canonical form of all the distinct primes and then increment each of the exponents and then take the product, and you'll get the total number of divisors. And if you'll notice right here, we do have 8 divisors. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now, again, the prime factorization is very useful in knowing when you're done listing the divisors here. Okay. Now, y'all, this is just more or less kind of going through and checking each one. The first one I noticed was k equals 5, and that happens when we noticed 1 plus k squared is equal to 26, right? Now 26 is a divisor in our list, right? And by the way, 1 would correspond to 0 at the beginning of the problem. The rest of these don't work out. That is, you don't get a perfect square. So you have to go all the way to 26 in our list here, okay? And of course, that does imply k is equal to 5. And I won't go through all the arithmetic. It's fairly straightforward, slightly tedious. But so for k equals 5, we get n is equal to 1025. And sure enough, if you go back and substitute it again, and I won't go through all the arithmetic, you get 25, which is, of course, a perfect square. 5 squared, right? Now, I only found one other. And you guys let me know if you see another. 9 is the next one because when you equate 1 plus k squared, 1 plus k squared, let's see, what do we need? I think we need 82 up here, okay? If you equate that with 82, that certainly implies that k is equal to the 9 you see right here. And if you carry on, you get 1053 for n. And so this is our answer, folks, 1053, and you get that it's equal to 9 squared right here. And y'all, I didn't show the all the work, but I tried it with all of them. All you gotta do is subtract 1. If you subtract 1 from 13, that's not a perfect square. If you subtract 1 from 533, that's not a perfect square. And if you subtract 1 from 1066, that's not a perfect square. These are the only two numbers in this comprehensive, all-inclusive list of divisors of 1066. And so this is the answer. 1053 is the answer to the question. It's a little bit bigger than 1025. So the answer is n equals to 1053. Okay, that's a pretty crummy looking in there. Let me erase that. Okay, so we got n equals to 1053. Is that right? I'm tired right now. Yeah, 1053. There was only two possibilities, technically three, but this zero case is sometimes called the trivial case, and we're not interested in that. Okay. Now, another question, how many times could this happen? It would be three technically. There's three ways that you can select an n to where this quotient is a perfect square. But this is just, there's probably two or three different ways to frame a question like this. You could list them all, whatever you want to do. Anyway, thank you for viewing.